I will begin with a word of prayer. So get up here. Heavenly Father, I thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray that you be glorified in what we do, and that we just understand a little bit more about generalized Stokes theorem and or how to set up triangulations of spaces and all these things, Lord. In your name I pray, Lord Jesus. Amen. So I guess I maybe should just I have an idea about sort of an intuitive calculation just to share, but I think I'm going to hold off on that and I'm going to stick to being organized in a more logical way here. And so, I mean, eventually we need to get back to just define like what's a manifold with boundary to set up the theorem properly. But I think this actually kind of leads to that anyway. And so what I'm going to cover for the time being is what you might call elementary homology theory. So this is taken from Paul Rentlin. So if I'm spelling that right. Paul, R-E-N, Rent-L-N. Rent. Oh, I did it wrong. Rent-Len. Nope, it's Rent, E-L-N. I probably always misspell his name. My bad. Oh well. Paul Rentlin. And this is manifolds, tensors, and forms. All right. I don't know if this is first edition, second, probably first edition. The subtitle is An Introduction for Mathematicians and Physicists. And, you know, it's a great book. He is a person who thoroughly understands both math and physics, and it's a joy to read this book as a person who finds I have divided loyalties, you know? But just to give you a quick overview of what we're about to do. The origins of topology, you know, really go back to Euler and others who were finding ways to, you know, count the number of like faces and edges on polyhedron. They like the Euler characteristic is something like an early result of topology. You know, you've seen the Königsberg bridge problem. You know, like how many different paths are there in terms of crossing bridges or not crossing bridges, these kinds of questions. And anyway, all of these things ultimately led to like systematic study of how to triangulate a space, right? And it turns out if you look at methods for triangulating a space, that naturally leads to this algebra, this homological algebra, which then in the 20th century was made more sophisticated with things like singular homology and then the de Rham cohomology and the homology versus cohomology. There's a whole other thing to talk about there, ultimately leading to the field of, you know, algebraic topology, which came into its own, you know, in the 20th century, I would say. But this is the sort of most basic version of that, and it ties into the question of how to understand Stokes theorem. See, because Stokes theorem, let me remind you, the goal, this is our target eventually, is to understand this. You know, the integral over the boundary of a manifold of a form is equal to the integral over the manifold of the exterior derivative of the form, right? So to understand that, we need to understand this notion of boundary for a space. And it turns out that if you talk about how to like approximate a space by its so-called triangularization, if you will, then the triangularization allows a really, really simple, purely algebraic characterization of the boundary. It's just beautiful, simple, linear algebra, really. And here's a quote at the start of his chapter. This is chapter 5 in Rentlin. In these days, the angel of topology and the devil of abstract algebra fight for the soul of each individual mathematical domain. The angel of topology and the devil of abstract algebra. I don't think he and Dr. Spranum would have got along. Oh. All right, so let's get into it. So here we go. Definition. C, an element, so this is all happening in Rn too, okay? So C, an element of Rn, an element. That's a subset. That's a subset. C, a subset of Rn is convex. Convex if for all x and y in C, all right, the line segment let's use the complex notation, right? Line segment xy, which is what? Tx plus, you know, t times y minus x, right? Such that 0 less than or equal to t less than or equal to 1 is what?
It's a subset.
Yeah, subset of C, right. All right, so he says, in other words, you can walk from any point in a convex set to any other point along a straight line and never leave the set. All right. So when I took graduate linear algebra as an undergraduate, which was maybe not the best of all my academic decisions, but that was, from my perspective, a fantastically difficult class because of the way it was taught, which is probably a lot like I teach. But anyway, he was always talking about the convex hull in that class. So it was you know, the convex hull. What is convex hull? Convex hull of a subset S, a subset of C of Rn, right, is smallest convex set containing S. I don't know if we have a notation for that in here. You might denote it. I think well, I better be careful not to step on the toes of the notation he is introducing that I've forgotten about. Uno momento. Por favor. Well, I think it is coincident with his notation. So I think we could probably. I don't think we're going to get into trouble, but I just small disclaimer. Hopefully, I'm not getting into trouble with this, but I probably would say, call it this for convex hull. So, for example, if we're in like R2, right, and I let S equal to, let's say, 0, 0, you know, 1, 0, and 0, 1, right? So 0, 0, 1, 0, 0, 1, right? Would it be the triangle? Yes. But what do we mean by that when you say the triangle? I mean, this is always an issue. When you say triangle, do you just mean the union of the edges, or do you mean the solid? The solid. You mean the shaded in triangle? Yes, indeed. Exactly. That would be the convex hull. This would be the convex hull of S. Of course, you could do things that are, you know, more curvy. You could do curvy stuff, right? Like you could do something like, I don't know, maybe somebody gives you a right? Maybe that's your set, right? So the original set, well, I'm not even going to shade the original. That's a hole, all right?
Yeah.
And so the convex hole of this would be like, well, I got to connect this point to this point, right? And so forth. So it's just going to fill that in. It's going to fill the eye in. And then, of course, everything else is already in the set. So,
Is the eye a hole?
yeah, the eye was a hole.
Yeah.
But it has to get filled in because, yeah. So the convex hull of Pac-Man is sort of like it depends on how I draw my Pac-Man, but maybe it's a disc. Yeah. All right. That's what a convex set is. All right. A polyotope is my example 1. All right. Definition. A polytope is the convex hull of a finite set of points. All right, exercise 5.1. Here's a finite set of points, and we take a particular convex combination of those, and yes. Okay, so this exercise might be worth proving. Let's state it as a theorem, okay? I will state exercise 5.1 as a theorem. So take a finite set of points, P1, P2, pk, all right? Subset of Rn. So this theorem, also known as exercise 5.1 in chapter 5 of Rentland, says that the convex hull of this, you can calculate it. And what it is, if you want an explicit formula for it, it is like this. The sum, how to write this sum? Yeah, sum over I of Ti Pi such that these coefficients, these T sub i's, they are between, they're non-negative, right? And the sum of them is 1. So this is interesting in its own right because this is the convex analog of the span. All right, when we talk about spanning in linear algebra, it's just arbitrary linear combinations. This is called a convex combination of the points. Convex combination. So it's not hard to see that this is going to give you, well, I don't know how hard it is, but we can prove that that is in fact the convex hull.
Why are we wanting a condition that equal to 1? I mean, I'm having a hard time visualizing.
Let's see here. So for example 1, maybe this is P1, this is P2, this is P3, right? So let's see. So in this condition, this situation, it would be something like T times P1 plus S times P2 plus R times P3 That's an arbitrary point, subject to what? Subject to the condition that t plus s plus r, little r, is equal to 1, right? So, all right, so to start with, if you look at special cases, right, like s equal to r equals to 0, t equals to r equals to 0, t equals to s equals to 0. So if that's the case, then the remaining one is t, it has to be 1, s has to be 1, r has to be 1, right? Which gives me the point, yeah, p1, p2, and p3. So you obtain the points in those special combinations, right? But,
So that shows that S is containing all of S.
yeah. Let's see, how do you... Yeah, and I guess if you take something like, I mean, just to see how it works, if I take, you know, like a half, you know, plus a quarter, you know, half of P1 plus a quarter of P2 plus P3 over 2, what would that get me? P over 4, right? For my example 1, that would be, well, P1 is stupid. I really should make the origin not be in a part of this example to make it kind of more obvious. Like, the more, you're not seeing the full glory of what this thing is with me choosing one of the points to be the origin. But anyway, probably makes my life easier. I'm not going to complain. But that is, so this is what, like, I guess it's 1/4, comma, 1/2, right? No, 1/4, 1/4, 1/4, yeah. Which is like cure, right?
Yeah.
And then, of course, if I was to put 2 of these coefficients to be 1, for example, that would get me up to, like, this point up here, right, would be like, you know, P2 plus P3, basically, right? And you can either do 0 times P1 or just P1. But of course, that's not allowed. And also, if that point was to be included, it's definitely not the convex hull, right? Because the pictured triangle is convex. So if I include that point, then, and of course all the other points leading up to it, well, it could still be convex, but it wouldn't be the smallest, yeah. But I think to really answer your question is to solve exercise 5.1. Because that's really what exercise 5.1 is inviting you to do, is to come to a more nuanced understanding of why that formula gives you the convex hull.
Are we going to do it, or should I do it as homework?
You can try to do it in a homework if you'd like. That'd be good homework to do. Sure.
Let's do it.
Yeah. I don't know if I formally assigned that or not, but it would be a good one to do. So it's on page 139 of Rentland. The full instructions here is to hint is use induction on K.
Induction. Okay.
Yeah, use induction on K. Like, I can prove the base case. It's actually, you can kind of see the base case, right?
The base case is just 1 point, P1.
Oh. Yeah, okay, fine, that's kind of dumb. Let's prove the, well, it's one of those things where I think maybe you want to look at the k equals 2 case as your base case. Not because logically it has to be the base case, but because pragmatically speaking, it probably is what you need to be able to see in order to make the induction step. So, yeah.
But yeah, the k equals 2 case is just a line segment from one to the other.
Right.
Which ranges them through.
Yeah, so if you had like T1, just what you said, T1 P1 plus T2 P2, such that 1 plus, excuse me, such that T1 plus T2 is equal to 1, right?
Yeah.
Then you can solve this and say, well, that's really T1 P1 plus 1 minus T1 P2, right? And then that is, you know, P2 plus T1 times P1 minus P2. So as T1 ranges from 0 to 1, we obtain the line segment from P1 to P2, which
Which is the convex.
yeah. And obviously, if you, I guess the question is, all right, sorry. Show the convex hull as precisely the set of convex combinations of the points. So, well, that shows that the convex, I mean, that does show that the convex hull of P1 to P2 is the set of convex combinations, that algebra, I think. So yeah, and then you want to assume it's true for k points and try to prove for k plus 1, right? But anyway, yeah. All right, I'm going to stop. We should go on. All right. Now, he says, let V be an element of Rn and A an element of the reals. And think about the usual Euclidean metric. Any set of the form all right, so he's going to define a so-called affine hyperplane. An affine hyperplane, he defines it as x in Rn such that oh, yeah, duh. X dot V equals to A. You know, for here A real number and V in Rn. So this would define a so-called affine hyperplane. Now he actually uses in Rentlen he uses a different notation for the dot product, but we know dot product, so I'll stick with this. All right. Now, so for example, if you're in R3, now I would say I think I want to say that to be fussy, I probably should assume V is not equal to 0. I don't think he says that, but I think that's probably a good idea. Because if you don't make V, I mean, if you let v be 0, and you also had a equals 0, then that gives you the 0 equals 0 equation, which is everything. And I don't think I want to say that all of space is in a fine hyperplane. I mean, I guess if I do, I can allow it. I don't know. All right, let's leave that open for questioning.
This is a fixed A, right?
Fixed A. So for example, 3, we could have like v is 1, 2, 3, and a equals to 4 in R3, right? And the x, of course, would be x, y, z, right? Dotted with 1, 2, 3 equals to 4, which of course is x plus 2y plus 3z equals to 4. The reason it's in a fine hyperplane is that it doesn't have to go through the origin. All right, like that 4 there. If that a is 0, it's a plane through the origin. Otherwise, it is not. But this generalizes this to n dimensions. So in 2 dimensions, they're just lines, right? 4 dimensions, they're volumes, so forth. He says it determines 2 closed half spaces, right? So the affine hyperplane, it's going to give us 2 closed half spaces, right? We can either look at the set, you know, x in Rn, such that x dot v is greater than or equal to a, right? Or we can look at x in Rn such that x dot v is less than or equal to a, I think is what he does. Yeah. And those are closed half spaces. And he says the affine hyperplane H is, oh, now he's going to make a definition. The affine hyperplane H is a supporting hyperplane of an n-dimensional polytope if H meets P in some non-empty set P and is confined to one of the half spaces determined by H. Oh, that's a mouthful. So definition. Here we go, let's try this again. H in a fine hyperplane, all right, is a supporting hyperplane of a given polytope. Let's call that polytope P. All right. If H meets P in some non-empty subset of P, and all right, P is confined to one of the half spaces determined by H. All right, and any set F, which is of the form P intersect H, where H is a supporting hyperplane of P, is called a face of P. All right, so if F is a subset of P and H intersect P is equal to F, then F is a face of P. At this point, it's probably good to give some more examples to try to like bring this definition to some more life, right? So let's try to do that. I usually do best in 2 dimensions, so if you don't mind, I will stick with 2 dimensions for the moment, at least to get started. Because they're, you know, the affine hyperplane is just a line. So example 4. So let me just suppose that our polytope is a triangle, right? So let's see here. Different things I could do. I could do like this, right? I could let that be my H, right? And let me give labels to the vertices. Let me call this V1, V2, V3, you know, and I'll call this edge 1, edge 2, edge 3 for not, you know, the edges. All right. So V's for the vertices, E's for the edges. So, all right, so V1 is a face of P. Okay?
V1
is a face of P because it meets H, right? And all of P is in the half plane up here. But of course, we could also notice that, like, if I look at this half plane here, right, this one, let me call this H2 for the sake of discussion. You can see then that, well, we could argue V1 is a face, V2 is a face, E2, that line segment is also a face, right? Because this closed half plane, all right?
So should we say with respect to H?
It's a face of P. So the face is not with respect to the hyperplane, it's with respect to the polytope.
Okay.
So let me just list them. What are the faces? Faces of my example P include the vertices, V1, V2, V3. E1, E2, E3, the edges, right? However, not included would be like interior points of the polytope, right? Like if I tried to find this as a face, that is not going to work because any hyperplane that intersects this interior point, it's not going to make the polytope just on one side or the other side of the hyperplane, which is a line here.
But what I'm wondering is when we say something's a face of the polytope, does that mean there exists a hyperplane such that?
Yes.
Okay.
Yeah, there exists. Not.
We don't fix one.
It doesn't have to. No. Yeah, the different hyperplanes for different faces.
Okay.
Yep. All right. So, oh, and the other thing I should mention, of course, P itself, right? Oh, wait a minute. Well, oopsie. Oh yeah. All of P itself. So I can't take an isolated point in here, but if I take the totality of it,
And what would be the hyperplane?
like H2. see, all of P is, P meets, see that like P is the entire, P is the whole set of points, right? So P meets the hyperplane H2 along edge E2, so it meets it. It's meet just means intersect, non-empty, okay?
It doesn't have to be like every point touch.
Right, yeah, it doesn't have to be every point touches. Certainly not. Yeah, it doesn't have to be every point touches. I mean, as he says right here, this definition allows for F equals to P. All right. Well, let me make sure that's the case. However, so a face, but these are the quote-unquote proper faces. Proper. So the face being P is I guess is an improper face. My extension of the language here. All right, let me go on here. The dimension of a face is the dimension of the smallest affine subspace containing it.
Dimension of the smaller affine space.
Containing it. Yeah. So I think at this point he's extended his meaning of affine hyperplane, affine subspace, right? Because affine hyperplanes are necessarily n-1 dimensional. So unless we're going to extend our definition of affine hyperplane to include other dimensions, the only way we could really give a dimension to any of the faces here at the moment is the edges. I mean, but anyway, the dimension, I'll just say this, the dimension of the vertices is 0. The dimension of the edges is 1, and the dimension of P is obviously 2. Well, I'm not sure that's right. Let me hold off on that. I'm not sure I could say dimension P is 2. He says a 0-dimensional face is a vertex, a 1-dimensional face is an edge, an n-1 dimensional face is a facet. And the collection of all facets of a polytope is called the boundary of the polytope. And the interior of a polytope is P minus its boundary. Because polytopes have facets or seats, they're also called polyhedra, which means many seats. The convex hull of its vertices, let's see here, it seems obvious that a polytope is the convex hull of its vertices and that every face is just the convex hull of some subset of the vertices, but the proofs are surprisingly subtle, so we will admit them. Yep. So, like here, the boundary of P includes, you know, the edges and the vertices, right? Let's see, what else can I say? Okay, I think I've said enough. Let me go on here. So we are going to assume the last sentence which I read, which is that any face of the convex hull is, any face of the polytope, of a polytope, right, is going to be the convex hull of some subset of the finite set of points which is generating the polytope. Like, yeah, like here, in this one, the convex hull of all 3 points is the triangle. The convex hull of points V1 and V2 is edge 2, which is one of the faces, right? But this continues to be true if we go into like higher dimensions. Like example 5, you know, if I took like V1, V2, V3, V4 in three-dimensional space, right? Then if you were to look at, say, for example, the faces of that are triangles, solid triangles, right? Like one of the faces is the front face. This right here, what we're claiming is that that front face you can actually obtain by the convex hull of V1, V2, V3. That's the front face. Call that face 1. But on the other hand, if I wanted the other one, this one over here, like face 2, I could obtain that by the convex hull of V2, V3, and V4. But Rentland warns, basically Rentland's like, this seems obvious that any face must be obtained by the convex hull of a subset of the points forming the polytope. But he's like basically warning that the proofs, to actually prove this, requires effort. So, since we're averse to effort, we're going to go on. All right, we good? Yeah. Okay. Now you might wonder where the linear algebra is going to enter in. There doesn't seem anything very abstract algebraic about anything we're doing so far, you know? Like this is all pretty just, what, concrete coordinate geometry stuff, isn't it? You know? I mean, so where's the abstract algebra? Well, give me a minute. It's about to enter the scene. So a set of points S equal to, we'll enumerate them from 0 to D, P0, P1, dot, 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 P sub D, all right? A subset of Rn, okay? Is a finely independent if P1 minus P0, comma, P2 minus P0, comma, dot, 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 comma, PD minus P0 is linearly independent. Okay? So you get what that's doing. That's exactly how we set up the, that's basically how you set up edges. Well, I mean, if you think about a given, let me just draw a picture. Right, if this is P0, and this is P1, and this is P2, and this is P3, and this is P4, we're desiring that the displacement vectors right, that the displacement vectors be linearly independent. What would it mean if they were linearly dependent? Well, first of all, if this picture is actually in R2, then they're linearly independent, right? Because you can't have more than two linearly independent vectors in R2, right? In the same set at once. I mean, of course you can, well, anyway, you know what I mean.
But it'd be that we can delete one of the points and still have the same convex hull. If they're dependent. Because one of them is going to be the edge already.
Yeah, yeah, I think you're right. I think if they were linearly, if they were finally dependent, you say you could eliminate a point and still obtain the same convex hull. That seems very likely as a theorem. I like it. I'm not sure it's true, but I believe it's true. I believe you're right. But the reason I'm not sure it's true is not because I've thought about these things deeply. I just haven't thought about it. Okay, so I'm not casting doubt on from the position of like a wealth of understanding or anything. Okay.
Yeah.
Next up, definition. A simplex is the convex hull of an independent set of points. And so, by the way, we will start omitting the affinely. All right, let us understand that if we talk about an independent set of points in this context, we mean affinely independent. All right. And he says, we write bracket S, all right, to denote the simplex determined by the set S. Rats. I chose poorly. I've been using Langle for that. I should have been using brackets. That's his notation.
Or the convex hull.
Yeah, so like he had, so I should go back here like that. Let me fix that. It's going to be an issue because he does use the angle brackets for other things later. So let's correct, try to get on the same page notationally as Rentland. So sorry, if I was more with it, I wouldn't have done that. No biggie. These are supposed to be square brackets for, and I guess if you really want to be really picky, I should put curly brackets because it's, you take the convex hull of a set, not of a list of elements. But let's not do that. All right, anyway, I'll be a little bit sloppy. All right, so anyway, so if the number of things in S is d plus 1, then oh man, I still did it wrong. I'm sorry. No, it's fine, it's fine. I'll get it eventually. I guess he doesn't have a notation. The dimension of the convex hull of S, all right, is equal to d. All right, so if you have 3 points, the convex hull that you generate from 3 points is two-dimensional. All right, great.
Is that a theorem?
Yeah, it's a theorem, sure. It's a theorem and a definition of notation all at once. So sorry. But in this context, this would be called, this is a D-simplex in this context, okay? So a D-simplex is one which is the convex hull of d plus 1 points. Okay. Now he lists some examples. A triangle is a 2-simplex. A tetrahedron is a 3-simplex. All right. Now here's another theorem. A subset of an independent set of points is itself independent. So if T is a subset of S and S is, you know, affinely independent, then that implies then T is affinely independent. That is, yes, another theorem, which is a close cousin to the one you proposed earlier today. Yeah. He says, because a subset of an independent set of points is itself independent, any proper subset T of S determines a lower dimensional simplex of T, which is necessarily a face of S. So in other words here, what this is going to mean for us is that the convex hull generated by T is face of S. And so like if the order of T is equal to K plus 1, then in this context, this is a K face of S. So we tack a K to talk about its dimension. So like in my example 4, the vertices are 0 faces, the edges are 1 faces. All right. For my example 5, that tetrahedron, you could talk about the sides, the ones I was looking at were 2 faces, the edges would be 1 faces, the vertices would be 0 faces. All right. Interesting. Exercise 5.2 is a kind of coordinate theorem. It's interesting. Theorem. It says this: if S is equal to, say, P0, P1, dot 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 PD, all right, then there exist unique T0, T1, dot 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 TD in 0 to 1. Such that, you know, the sum of the I of T sub I is equal to 1. And well, if P is an element of S, right? Not S, but the convex hull of S, I should say. Such that there exists unique blah 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 for which P is equal to the sum I equals 0 to D of T sub I, P sub I, right? So this is exercise 5.2, which is sort of like the, you know, uniqueness of if you use a set of linearly independent vectors, they form a basis for the span of those vectors, and the coordinates with respect to that basis are unique based on the independence of the vectors. Well, likewise for the set of points, the convex combination that forms a point in the simplex is unique. These are called quote-unquote barycentric coordinates of P. All right. He says, remark, as we have defined them, geometric simplices are closed subsets of Rn. Given an independent set of points, P0 through Pn, one can also define the open simplex to be the set of all points where you have positive coefficients and they sum to 1. All right. So open simplex doesn't allow for coordinates to be 0. The barycentric coordinates can't be 0, which isn't going to let you isn't going to let you actually get to the to the faces. You know what I mean? Like if you look at how we attained the vertices, it was by putting some of the barycentric coordinates equal to 0 and one of them equal to 1. So if I have all of the coefficients, all of all of these are positive, then it's a fuzzified simplex, basically. It's quote-unquote open simplex. Yeah. All right. And of course, then you can also talk about open faces and blah, 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 blah. He says the open simplex S is the topological interior, and he has a notation for it. The open convex hole is this. That's kind of cute, isn't it? So this is a subset of this, right? And in fact, the interior of the simplex is that. So it's a kind of cool way to, get the interior, I suppose, topological interior of the simplex. And then another way to look at it is that the simplex is the closure, the topological closure of the open simplex as well. All right, so finally, we're about there. We come to the main definition. We still haven't come to the main definition, but I don't rush these things, as it's important for us to take our time on this stuff. Otherwise, it makes, when it gets abstract, all of a sudden it gets really hard to follow. All right, so I've been slow. Let me go on. The main definition. I need a place to write it. I think we can do it over here now. Be okay. Well, I can't go too fast because I don't have much material left for this semester. So if I go too fast, then it'd be very embarrassing. Nothing to do. So definition. This is the definition of a simplicial complex. A simplicial complex K. A simplicial complex K is a finite collection of simplices. Finite collection of simplices. Did he tell us what a simplex was already? Oh, yeah, I just wrote over there, simplex. So simplex is the plural of simplex is simplice, all right? All right, great. I'm sorry, I'm just a dummy. Duh. All right. It's a finite collection of simplices satisfying a particular set of rules. Really just two. If you have such that, number one, if the simplex generated by S is an element of K, and T is a subset of S, all right? And he does use this to mean proper subset, okay? Yeah. If T is a proper subset of S, then the convex hole generated by T is also in the simplicial complex. It's also in K, all right? So in other words, this says every face of a simplex in K is a simplex in K. Every face of a simplex in K is likewise in K. All right? And number two, for any S1, if you have two simplices, one generated by S1, other generated by S2 in K, then if you take the intersection of these two simplices, which we can